Thank you, everyone, for joining this talk. This is about evolutionary machine learning for business optimization. As Heidi mentions, I have the backgrounds in AIs and operation research, and also did earlier degrees in industrial management and optimization as well. So it's lead me to my current research topics. Research focus is looking at the interface of AI and optimization and see how AI can further help promote or also enhance the performance of optimization, make optimization more approachable to business. So the topic here, talking about evolutionary machine learning is which means the machine learning, but inspired by evolutionary computation approach. And so I'm going to share a little bit about what I'm thinking about this domain and also some case studies in production schedulings, which is one of the key problems that I work with for the last several years. So it's a quick outline of this talk. I just briefly talk about business optimization problems or optimization in general. So I'm going to go through this one very quick, given that we have a great audience with a lot of experts in optimization. I don't want to talk too much about this one. A bit of a reflection on the optimization approach, algorithms in the past and present, and also the challenge of applying those optimization algorithms in our large scales and tricky optimization problems. Talk about the role and also how current AI machine learning can be used in optimizations. And they're going to provide case studies, and also at the end, I'm going to discuss some of the opportunities and challenge that we may face. So things all of us here, I think we work a lot on optimization problems, and most time we got mathematical optimization problems. Many come from mathematical programming backgrounds in which you're going to work with wide range problems, formulate into the format in which we all, I think we in here in these communities, we all agree that optimization have a wide range of business or real world applications. So, and that is things that is where I like my interest, and this is where I want to go further in my career as well. And so for optimization problems, we want to look at some key things, including the objective functions, the constraints, what we needed by the real world applications. We look at the distinct variables, and also so we look at the data by itself. So all of those things put together is going to help us understand, formulate an optimization models, which we try to solve, we try to deliver the best possible decision values. But before I go further into the key topic, I just want to take a step back and look at the methodologies that we use so far in either operation research or in optimization domain. So I look at here as one of these various old frameworks from we look at the operation management, but on the quantitative end. So it's very close to what we're doing. So in this framework, it says like how we're going to go about and find a solution for problems, real world problems. And so usually it's when we look at real problems, we try to understand, we talk to the stakeholders, we talk to decision makers, we talk to operational operators, we try to understand systems or the problem that we're going to work with. We try to best conceptualize the models, come up with conceptual models. And this is where we can easily communicate and talk to the stakeholder, try to understand and see, and try to validate and see whether things are well formed. Then with the conceptual model, we try to come up with scientific models. It can be a mathematical models, in a format that can be of interest, it can be used for solving. So a lot of us here have been using mathematical programming. So you formulate a lot of problems in linear programming, using linear programming, mixed integer linear programmings, and such. So those are kind of scientific models we're talking about. And we then, after we have the models, well, we try to we ask the question of what is the best, the best solution, what the optimal solution there. So we go to model solving, and hopefully we're going to end up with some reasonable solution, optimal solution. That before we verify and try to implement those solution and observe, see whether it's actually help us address the real world problems, or whether we need to go take a step back and try to modify the models to better reflect the real world situations and have so that we can come up with a more acceptable solution. So we can look at this. What I like about this model is that we can look at from different angles, where there are different small loops in there, including the loops on the right-hand side from conceptual models, scientific models, solution, back and forth. A lot of us actually is working in that small loops where we have the models, abstract models and mathematical models. We're working a lot to try to find the best solution. But a lot of other people, they look at the broader loops, bigger loops. They try to incorporate and try to, at the end of the day, we try to deliver the solution that actually address the problems. And this can be very messy. Sometimes we cannot even achieve the optimal solutions. I also look at the way we solve optimization problems from the algorithm's perspective. So again, we start with the real problems, especially for the researchers working very heavily into algorithms and optimization solving techniques. And there's a different way for you to start. You're going to start with building mathematical models, computational models. It depends on your expertise and your interest. And we can look through the theories and try to design a good solution methods to solve the problems. Sometimes we also need to implement the algorithms and deploy the algorithms. At the end, if we writing papers and such, when we need to run some experimental analysis, try to see where there's the algorithms we design offer the good solution and efficient enough. Some other people also look at the shortcut and says if what are certain problems, then they can look at a quick solution, something from heuristics and rules. If they work with the problems for a long time, if they collect enough experience, they usually come with very reasonable heuristic or rules that may or may not have the theoretical support, but can work reasonably well given certain assumptions about the problems or the environments that we're going to work with. So, and these quick solutions then is great shortcuts to go from real problems to algorithm implementations and experimental analysis. But when there's growing number of solution methods, and even that either it's going to be the exact methods or heuristics, there's a lot of decisions there. There are a lot of directions that we need to look at after we do experimental analysis, whether we want to build a better one, what kind of problems, constraints that we have not yet addressed, and how we're going to go about and solve those problems. So one of, as I mentioned, I came from industrial management backgrounds, and one of the things we work a lot with, we look at the system and system theories. And what I like the most when try to addressing the problems is I want to have a holistic view of solving the problems, not just solving the problem itself, but also other aspects that might impact the way we models and solve the problems. And the way I want to look at things as systems is to look at the bottlenecks, where we may have problems, where things can be slowed down. If we're able to successfully identify the bottlenecks and invest enough efforts and time into that, try to shift at the bottlenecks, or try to improve and make it more efficient. then we actually is going to help with the entire effort of solving the optimization problems. And if you work in optimization domain across different tasks, then you will realize that we have different bottlenecks there, always from the modeling parts, where try to understand the problems, the choice of modeling techniques, always to experiment things, model solvings, or even at the end, after we're able to get the solution, there's also had the bottlenecks of how we're going to communicate the optimal solutions effectively to the stakeholders or decision makers. So in terms of optimizations algorithms, now I'm going to go through this one very quickly because I believe the audience are very familiar with these techniques. It's going to be traditional mathematical programmings. They are well set of forms that we're able to solve the problems very efficiently, and they're very popular. But there's going to be things for like constraint programmings, in which we're able to easily formulate a wide range of problems and also in using very user-friendly language, and able to solve that in very efficiently. And there's also going to be meta heuristics, which also a broader domain. I also work a lot with meta heuristics in the past. We look at a number of either nature-inspired, evolutionary-inspired, or bio-inspired kind of techniques, and try to employ, try to apply those concepts, try to come up with such techniques that are able to find a good solution. Not most time we cannot guarantee that it's going to be optimal, but experimentally in experiment we figure out that they provide very good near optimal solutions. So there are different meta heuristics. There are others in the literatures, including semantic neuralink, double search, evolutionary algorithms, or swarm intelligence, including ant colonies and particle swarm optimization. But the challenge of even those where we have a lot of way to solve the problems, there's still quite a lot of challenge that we still need to work with. I think the more challenging one probably is with the discrete decision variables. So we need to talk about the combinatorial optimization problems, in which is the standard solver or the standard mathematical programming approach. In many situations, in many occasions, have troubles finding very good solution, and sometimes they can also only work with very small or medium instances. The second one is more about uncertainties, when we try to incorporate random sources and try to make predictions and try to incorporate the prediction into our optimization problems, is present a wide range of challenges and also add to the complexities of the solving process. It's still, I believe, this still very active research areas. And finally, is last but not least, but is look at case studies when we have a lot of constraints, especially in the situation where the problem you solve is in the environment where a lot of rules, a lot of constraints need to be applied in order to come up with a feasible solution, either to address the technical requirements or just to make the stakeholders happy. So there's a big field of constraint programming with a lot of solvers available in order to help us solve these problems. One of these areas I look a lot in my earlier in my PhD studies and later on in my academic career is I look at heuristics, but I look at heuristics from different angles. And I start with like heuristics, when we refer to experience-based techniques to find good, reasonable solution for some special cases. It usually is going to be some approach that can be very quick, but there's no guarantees on the qualities of the solution. Then about a few decades ago, then there's going to be the invention of meta-heuristics, where they look at the more generic optimization methods that can deal with a wide range of optimization problems. But similar to heuristics, there's no guarantees on the optimalities of the solutions. And also, but the good thing is that compared to heuristics, meta-heuristic can be a lot more generic. It can be generalized. It can be reused for many problems. And more recently, is there another direction they call it hyperheuristics. So is look at the problems from heuristic search space rather than the solution search space that most time we're looking at. So most time we look at meta-heuristics, or even with the traditional optimization search, we try to navigate through the solution search space and try to improve the solution over time using some smart intelligence operators. But for hyperheuristics, they look at the heuristic space. The question is, can we somehow search for a heuristic that can offer very good solution? And sometimes it's actually we're able to even identify the heuristics or the optimal way to solve the problems very quickly. So by looking at the heuristic search space, then we can train, we can try to do most of the heuristic search offline. And then when we come up with a heuristic that we well justify, well verify that it's going to perform well across different subset of problems or instances, then we are going to apply that when the situation is needed. So because I work in business analytics, so one thing interesting is we always looking at how a lot of things like big data, fast changing environments, and how they can impact optimization. So one of the key interesting things that our big data analytics able to offer is allow us to understand about environments in a much deeper levels. So instead of just looking at the operational data, they also may also allow us to look at things for like sentiments, this thing for like these low levels behavior or patterns, and also things for like data streams is allow us to continuously monitor the performance and also see what's happening in a system in real time. So giving a lot of those capabilities, we still have a big challenge in optimization, because in order to take advantage of those advanced big data analytics techniques, then we need to come up with a way to optimize things a bit more efficiently. We need to able to formulate and solve problems a lot faster. Otherwise, we cannot take advantage of these big data analytics. And put it simply, if the situation change, the environment change, we're able to understand the change, but with that we cannot come up with the way to even models or solving new optimization problems on time quickly, then we not actually take full advantage of the big data world out there. So there is a number of initiatives that looking at applications of machine learnings in order to help us solve optimization problems. And there's good motivation behind, and this is still looking at the traditional optimization techniques, different kind of heuristics. But the idea is to see whether we can learn, we can use machine learning in order to identify the patterns that are going to be helpful during the problem-solving process. So there's a lot of existing studies out there. Most of the time is still within this research space. And there's a recent paper in eJournals from Yoshua Benjios and others authors try to categorize how machine learning can be useful for combinatorial optimization problems. So they classify that into the existing studies into 3 groups: end-to-end learnings, So it's more like we use machine learning to actually help learning rules or heuristic that can construct a solution directly. So by the name of it, then you can see that there's no much guarantees of whether this generated solution going to be optimal or not. The second category is that have been looked at in the paper is to learn to configure optimization algorithms. Most time when we work with operations research or optimization techniques, that to solving a bit more efficiently, we need to tweak, we need to configure, we need to adjusting a little bit along the way based on some either systematic experimentations or based on some theoretical support. So machine learning, if they learn directly, is by solving a lot of instances, they may pick up what is the patterns that are required to help us determine what is the best way to configure our optimization algorithms. And finally, the last category is with the machine learning alongside optimization algorithms. So it's rather than at the surface level, try to make a small tweaks into the optimization algorithms. This last direction, they try to look at the optimization solving process, the search process in a more dynamic way. So that during the search or the solution findings process, machine learning can be used to make decisions or maybe sequential decision along the way. So I would say the last category is the more challenging one, but it's probably also the one that provides the greatest advantage if we think about the application of machine learning to combinatorial optimization. So I have my own views about handling bottlenecks in optimization with AI. Again, I look at the pictures of how we traditionally solving problems. We have real problems and we try to model it using our favorite modeling approach. Sometimes I like to use discrete event simulation. Sometimes I use networks. Sometimes I use just common mathematical programming models. Then when I come with the models I'm happy with that reflect well on the real world situations, they had to spend a lot of time developing solution methods. And sometimes if in the past that they're going to take the entire PhD thesis in it to solve one particular problems. And hopefully by the end, if we come up with a reasonable solution, we're able to validate and apply it to real world situations. So my research more focused on what we call AI-assisted optimization. So I look at still the modeling part is not changed too much, but instead of I myself need to look at these development of the solution methods or algorithms, I got to rely on AI to help me generate the solution methods. It's either be heuristics or even the optimization search algorithms. And I can, if I'm doing smartly, I can use AI to generate such very beautiful, efficient solution methods that not only is efficient, but also is robust against dynamic changes or uncertainties. It's going to be scalable, and also what I like also is able to provide certain level of interpretabilities of the solutions. So I kind of move and kind of shift the bottlenecks that we have earlier. When we work directly in models, we do a lot of trial and errors, take up time to reasons and try to come up with something good. I shift that part to AI and allow us to work directly and intensively with the models that we built earlier. And whatever is helped, we're able to spend time to validate the solution, and we can make some, give them a bit more input or reconfigure the AI so that is provide the solution that we really want, and we can apply them. So by shifting the bottlenecks, yes, we can save the time required to move from the earliest conceptualization into the implementations. Okay, so now I dive directly to one of the case studies I work a lot with. This is where most of my publications come from. Because my background is in industrial engineering, industrial management, so I work a lot with production and manufacturing environments. And one of the environments that I particularly have great interest for is the job shop models, job shop schedulings. This is a situation where you have the jobs or the customers' orders arrive at these manufacturing or production facilities. And in that environment, you have a number of machines, and each machines need to want to process it in order for an orders or a job to be marked as completed and delivered to the customers. They need to go through a number of steps within the environments. And after they finish by this first machine required, it's going to move to the next machines. So each job's can have different routes, and they need to complete everything. And we hope that we're able to solve the problems, and we're able to dispatch the jobs, do sequencing, arrange, allocate job to machine in a way that is can achieve an objective interest. I like this problem because it's have a lot of interesting constraints, including precedent constraints, and also have a lot of multiple conflicting objectives, reflecting the real world situations. And last but not least, we can say be hard problems. So there's a lot of space for us to explore the solution methods. We have a survey papers a few years back looking at the applications of one of the evolutionary based machine learning approach called genetic programming. And we come up with a framework, a unified framework in what they call at the time. I think it's going to be upgraded in the next few years as well. Is we look at the production scheduling problems. And in these methodologies, we start by looking at the meta algorithms, basically captures how we want to solve the problems. And that's in the meta algorithms, they're going to be the part that kind of fix. We know very well there's not much thing can change, but they're going to still going to be the components in which there's a lot of space for us to adjust, to adapt, depend on what kind of problem or instances that we have to deal with. So there are going to be different components that may impact how we solve the problems. So after we identify what components we want to solve or we want to find, we want to evolve, then we try to come up with a representations, a way in which this component can be represented in computers. It can be a trees, it can be vectors, whatever it is. Before we push that into the evolutionary search process. And of course, we need to have the evaluation models that help us justify whether the meta algorithms with the evolved components do a good job or not. And you go through this evolutionary process for a few rounds, and we expect to get it's going to get better over time. So in this talk, I'm going to talk about two versions of these problems. One is with a static version of job shop scheduling, and another one is the dynamic version of job shop scheduling. There are very interesting stories in the way that we approach these problems. But earlier when I did my PhD, so I think it's good to start with the static problem because it's well studied in the literatures. So we have a lot of things to compare with. And later on, then we also look at the dynamic situation because it reflects the dynamicities of the problem in real world. And there are going to be many more challenges that we have to incorporate. So for the static problems, there are a wide range of solution methods being proposed in the literatures. But in here, I look at mainly look at the constructions heuristics, and also improvement heuristic in some way, and also how I look at how we can make the optimization solver a bit more efficient when it's come to solve these kind of problems. So the pictures on the right basically is giving examples of very simple job shop scheduling problem, a static version at least. So you're gonna each job 1 to 3 gonna have different routes, and they have different release time. They have different processing time at each machines. It also have the way to see to tell about its importance, its significant, and it also have the due date in which you need to deliver. If you complete the jobs after the due date, then you need to you're going to have the penalties either in the form of tardiness or in some other form. So one of the solution methods I really like when it comes to job scheduling is the construction heuristic, or more particularly in this domain, they also call it dispatching rules or priority rules. The rules or heuristic in this case is very simple. When there's a queue in front of the machines, they're going to come up with a way to assign priorities to all the jobs waitings there. And the one with highest priority is going to be the next one that's going to be fed into the machine and get processed. So the idea is very simple. It's just priority-based scheduling. But the question is that how can come up with a priority function, a good priority function? And hopefully, somehow it's very close to optimal solution. So obviously, in this case, if we go with this type of construction heuristics, the dispatching rule that we use, the priority function that we had, that we use, is going to decide the qualities of the constructed schedule. So there's a few dozens of dispatching rules been developed by operation researchers in the literatures, and it can be extremely simple and it can be very complex. For example, there's small tables there showing like on the top two very simple rules. The first one, the minimum slack, is only look at how close it is before a job going to be late, and I use that as the priorities to pick the jobs to be processed. So it's very useful to reduce the tardiness of the jobs. And another one, the second one is what they call the shortest processing time. They try to make sure that the jobs that have high importance, they're able to process quickly, and it also focus on the one with short processing time, because it helps us clear out the number of jobs in the system very quickly. And the last one actually is a combination of those two, and also was a very popular dispatching rules in the literature. They call it apparent tardiness cost. So if you look at that functions, the final one is just a way to combine the two top rules. So the question here is it possible to design a better priority function? Or the bigger question is how we can do that automatically, because in the past they need to rely on the operators or the managers' experience in the system to come up with those kind of rules. So that's why I call heuristics. But it's going to take a lot of time to explore those things, a lot of trial and errors to come up with a good one. But given the current state-of-the-art AI, machine learning, can we do better? And because it's always relied on trial and errors, we try, and if it's not good, we try to improve it, or we try to pick up the patterns in which we can come up with a rules, good one. So it's quite similar to a kind of a machine learning approach. So I stick with the priority functions. And one of the approach I use to help me discover the priority functions automatically is what we call genetic programmings or evolutionary machine learnings. I like this approach because it's basically try to come up with, try to discover priority function in the format that quite close to what people have been developed in the past. Basically, it's just some mathematical expression. So if you're into math, and for each expression, you can easily represent them as a tree with root nodes and some leaf nodes, and with terminal or non-terminal nodes. For examples, in this case, you have if you have one small trees on the top right, W divided by processing time, weight divided by processing time. It can be represented as trees, and we can easily translate them to mathematical functions. And we can use that actually to identify the priorities for the jobs in front of queues or in our meta algorithms. And if you want to come up with a more complex mathematical expression, is going to be quite easy. So we have a number of ways to create the variations of those trees. And when it's come to genetic programming, because is one algorithms within the bigger evolutionary computations communities. So it still rely on evolutionary principles. It starts with the populations of different individuals. The only difference is that in this case, each individuals represent mathematical expression. And we start with, at the beginning, we start with initially random groups of mathematical expressions. And then over time, we then for each of the existing individuals, the mathematical expression we apply to the problem. It says with that priority functions, whether it's able to deliver a good solution, we can just we can assess the qualities of each mathematical expression by the qualities of the generated solution. So it can be done quite straightforward. And after we have the qualities of these expressions in our populations, then we can rank them based on their fitness, their qualities, and the one with the good performance, we try to pick them up and apply some genetic operators. But we borrow the ideas from evolutionary theories. So we can come up with something like subtree crossover or subtree mutation. The main idea is just to create some variations, to introduce some variations so that we can come up with a new population with brand new mathematical expressions. And because the one that we try to use for crossover mutation, this come from good individuals, we expect that over time, they're able to pick up and combine the good patterns that can actually help us address the scheduling problems well. We apply these ideas to job solve scheduling problem. We test that with a number of benchmark dataset and compare with the existing heuristics and also some others methodologies and also the exact method as well. So and we see that the evolved heuristics, the symbols mathematical expression discovered by genetic program actually work very well. They is able in some situation is provide the solution that very close to the optimal solution as well. But again, there's no guarantees on the qualities. This already most times can only be done through experimentations. So we come up with a wide range of ways in which we're able to utilize that basic concepts using genetic programming or evolution machine learning to discover heuristics in the form of mathematical expressions. And we apply that in to come up with improvements heuristics, sometimes with something that we can quite similar to greedy local search approach. But there's a lot of problems there, including the part where we need to adjust the meta algorithms. So it's not always going to be straightforward. So recently we look at a way to apply the same ideas, the same principles, but to existing optimization algorithms or solver. So in this case, we look at constraint programmings, and because I think it's quite a nice way to if it can be applied to something well established, like constraint programming is going to be quite useful to make the methodologies easy to be adopted. So and one advantage with using constraint programming is that we can utilize the formulation languages, these CB's languages to formulate the problem easily. So instead of writing the meta algorithms, it takes time to write the algorithms, the code, and also to validate them using this existing language. It can be in inert format. It's very straightforward, and it's also quite easy to verify and validate. So we come up with a new framework in which we got embedding the ideas of mathematical expression for priority rules to constraint programming. One interesting we identified earlier is that we can the way that CB doing the searching is involved a lot of variable selections and prioritization as well. So we applied these priority rules here to help us identify which variables we need to visit first when we solve the problems here. And we come up with some good results. In many cases, we're able to identify, we're able to reduce the searching efforts of CBs. It can be, in some cases, can be 10 times faster than the default settings of the CB solver. In many situations, we are also like if it's a problem very hard to solve or is to prove the optimalities, then in some situation we can prove the optimalities a lot faster, or quality solution is going to be a lot faster. I don't think I have time to talk about the dynamic job shop part, so I'm just gonna skip through this part and just gonna wrap up my talk. But for the dynamics job shop schedulings, then we done decent amount of work, and most of those have been published in one of our papers. One of the part that we also work pretty hard on is how to incorporate ideas and also include the human in the loops rather than just the problem itself. So we are solving and identify the solution methods. We try to get input from the user as well. And recently, we also apply the same ideas, but we look at how to make it search a lot faster, how we can transfer the knowledge across different scheduling tasks, how we can be up with a smarter generic operator so we can come up with better rules, better mathematical expressions at the end. We also have applied our algorithms to different optimization numerical including numerical routings, mining optimization. So to wrap up, there's still a lot of space to explore the different direction we can do it now. But given the current advance in AIs, I would say AI can still play a very big role in to help us speed up these algorithms design process. And it can reach out not just the part about developing solution methods, but also going to help with modeling and also validate, apply, and even help with the solution communications. Thank you.